Okay, welcome to lecture here. We'll get started in just a sec. We're continuing on in chapter 10, I believe. And where did I put that? There it is. All right. Okay, so we're on chapter 10. We were talking about last week before the holiday on Monday. We're talking about heat and specific heat. So remember that there is a sort of specific heat equation, which is Q is equal to ms delta T. Q here is heat or energy. And usually in units of joules or calories. M is the mass, and that is usually in units of grams. S is our specific heat capacity, and that's the one that has all those units. The joules per gram per degree Celsius, or if you're doing calories, calories per gram per degree Celsius. Our delta T here is our change in temperature. So that is our final temperature minus our initial temperature. And one of the few places in chemistry, as we talked about, that actually you will leave it in degrees Celsius. So you don't actually convert it to Kelvin or anything like that. And again, you leave it in degrees Celsius, and that will get you that. And we use this equation really to sort of calculate the heat or energy that's happening in a system when we are in the same phase and we're changing temperature. So as something sort of either loses some energy, gains some energy, we use this equation if the substance is the same state all the way through. So for example, if it's liquid all the way through, or if it's solid all the way through, whatever it may be, we use this guy here for just changing the temperature. This is what we're looking for. Now, we also talked about the idea of the value that you get. And if Q is negative, it means it's exothermic. And as we've been talking about in this chapter, exothermic means that heat and energy is released. So something gives off the heat and energy, the energy value will be negative. And if we do get a positive value for Q, for example, that means that it's an endothermic process. And that means that heat and energy is being absorbed. And we talked about sort of the conservation of energy. So it's really sort of that simple idea that if someone loses a certain amount of energy, something else will gain the exact same amount of energy. So we don't lose or create energy along the way. It is just transferred from one place to the next. And the only difference really in sort of that conservation of energy is the sign, is sort of how it's represented. So again, if somebody loses, say, 5 joules of energy, if you did a calculation, it would be minus 5 joules. If somebody gains that same amount of energy or absorbs that same amount of energy, it would just be a positive 5 joules. So again, that negative and positive value, whenever you calculate anything involving energy, is really important to have on your answer, because it does indicate whether or not the sort of process there was exothermic or endothermic. Any questions on that stuff there that we talked about, I think, at the end last time? So to take sort of what we've been talking about with this sort of to the next sort of step here, and a reminder as well, a couple of other important things that we talked about. Specific heat of liquid water is at 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. And again, that's specifically for liquid water. If it's, say, gas or ice, it will have a different value. And that's also the conversion that's commonly used as well, that there are 4.184 joules and 1 calorie. And remember, when we're talking about these type of calories here, that's sort of energy calories, as opposed to capital C, which is more of those nutritional calories, which is 1,000 of these little guys. So those are a couple other important things that we talked about, I think, last week as well. Now, what happens if we, and it's a very common sort of procedure, that sort of transfer of energy that occurs. So for example, let's say I had a bucket of water here. And let's just say I had 150 grams of the water. And let's just say that the initial temperature of the water was 25 degrees Celsius. And let's just say I had a piece of metal here. And let's say the mass of the metal was, we'll make up some numbers here. We'll go with 98 grams and hope for the best. And it had an initial temperature of, say, 92 degrees Celsius. And if I dump the hot piece of metal into my water, it's going to cause a couple of things to happen, right? The metal will lose some temperature, right? The water will gain some temperature along the way. And let's say that when I did that and I threw it into here, the final temperature of the water went up to, say, 28 degrees Celsius. And if I want to know what the specific heat capacity of the metal is, I could sort of figure that out based on this sort of relationship of conservation of energy. And the idea here is when the metal goes in, it's going to lose a certain amount of energy. And all that energy is going to be basically picked up by the water that's there. And that's why we do see the water's temperature start to rise. So in terms of the water, if we look at the water part, we actually can do Q of the water would be our mass, which would be 150 grams. Our specific heat capacity, 4.184. I run out of room there. And our change in temperature went from 28 to 25 degrees Celsius. And if we do that calculation there, we end up with, let's see. We'll go with 1,882.8 joules would be the answer. Again, Celsius would cancel, grams would cancel. The only thing left is the joules that was there. In terms of sig figs, truthfully, in terms of sig figs at this point, it probably would just be 1. So we'll round that off to, we'll just call it 2,000. Based off of this subtraction here, when we subtract these guys, we end up with 3, and that's 1 sig fig. So we'll just round it to 2,000 for the sake of argument here. Now, what that means is the water here, when the metal went in, gained all that energy, that 2,000 joules of energy from that hot piece of metal that was basically tossed into the water. Now, it is positive here, right, for the water, right, because this is a endothermic process. The water gained all that energy. All that energy that the water gained in this particular case had to come from the metal. So the metal is really the source of all that energy that was gained from the water. So there is sort of a relationship that Q of the water, for example, would equal minus Q of the metal. And what that means is the metal would have lost the exact same amount of energy. The only difference is it is exothermic for the metal, which means for the Q of the metal, it would actually be minus 2,000 joules. Again, the exact same value because there's that conservation of energy. The negative here basically indicates that the metal has lost that amount of energy, and that's why it is negative. Any questions on that so far? So if we think about what we got going with our metal at this point, for our metal, we have 98 grams, right? We have the 92 as our initial temperature. We have now figured out that the metal lost 2,000 joules of energy, which would be equal to the amount of energy that was gained by the water. And the last sort of piece of information that we're missing to allow us to solve for the specific heat capacity of the metal is actually the final temperature of the metal. So if you think about it, if I toss this piece of metal into this water and it just now sits there, right, in the water, at some point, what's going to happen is the piece of metal and the final temperature of the water will be the same because it's sitting in there, right? They'll come to equilibrium in terms of the temperature, and that piece of metal that's sitting in that water will eventually come to rest at the same final temperature as the water ended up at. And again, because it's basically sitting there. So, if you put something into a glass of water, it's eventually going to come to the same temperature as that water. If you have a bucket of ice and you put something in the bucket of ice and just kind of left it there, it would eventually come to the same temperature as, say, the bucket of ice. So it's sort of the same idea. So in this case, in examples like this, the final temperature, something like the water, is always going to be really the same temperature as the object or the piece of metal. It's usually metal they throw in these things. Metal that you kind of put into the water, again, they'll come to rest at the same temperature. So from the information from the water, we know that the final temperature of the metal is actually going to be 28 degrees Celsius. And now if we think about Q of our metal, we have ms delta T. We have the Q of the metal. We have the mass of the metal. We have the change in temperature of the metal. That's going to allow us to actually solve for the specific heat capacity of the metal. And that would be S is equal to Q of the metal divided by m delta T. Again, bringing these guys on the right to the other side by dividing. And if we put our numbers in there, we get S is equal to negative 2,000 joules divided by our mass, which is 98 grams. And our change in temperature here, and this is important why we talked about doing final minus initial. Our final temperature of the metal after it cooled down is 28 degrees. Our initial temperature is 92 degrees. And that's going to give us a negative number, which is important because that negative number and this negative here will turn our specific heat capacity into a positive number, which is what we need. So in this case, we'll see how bad I did when I made up the numbers here. 2,000 divided by 98 and divided by 28 minus 92. And that gives us a specific heat capacity of like 0.3 joules per gram per degree Celsius using the 1 sig fig that I had in my bad made up numbers earlier here. But more importantly, any questions on that calculation? So there really is sort of that relationship that's oftentimes sort of said that the Q of the water is equal to minus the Q of the metal, or it could really be any object. And what that really means is both of these Qs are equal to the specific heat capacity, which means essentially you can take the mass of the water times the specific heat capacity of water times the change in temperature of water, and that would equal minus the mass of the metal times the specific heat capacity of the metal and the change in temperature of the metal as well. So you could kind of set these guys equal to each other. The important part is really you got to distribute a negative in there, and that's what gives it sort of the opposite relationship there when you put those guys together. And it allows you really to follow what happens when you, say, throw a piece of metal in there. I did it kind of in parts up here. You could have just plugged and chugged everything into this equation here. Let me kind of write that a little bit better. And solve it that way. Or you could kind of do it in parts with that idea that there's no loss of energy. So everything, whatever is lost is gained by the metal. And it doesn't necessarily always has to be a metal. You can actually do this, for example, if you've poured water into water. It works the same way. One water is going to be hotter in temperature, one's going to be colder in temperature, and they will come to rest, at a final temperature that's the same for both of them, again, because they'll be in the same glass or beaker or whatever it may be. Any questions on that? All right, so why don't you try one here? And of course I did that here. So once you do the one that you have next, which I'll just write on the next page, you have 100 grams of water at 90 degrees. It's added to 100 grams of water at 10 degrees Celsius. What is the final temperature of the water? So you got 100 grams of water at 90 degrees Celsius. It's added to 100 grams of water at 10 degrees Celsius. What's the final temperature? So give that a go, take a couple minutes and see what you come up with. Again, mathematically here, you could do it just like what we were just doing with that equation with the water and the metal. It's the same idea. You just think of the hotter water as the metal going into it. So see what you come up with. And I'll show you mathematically how you actually solve it here in just a second. Okay, so let's take a look and see how we're doing. So although it's not really like a piece of metal going into water, it's sort of the same idea. We have some water here that is obviously hotter in terms of temperature. So we have 100 grams of this water at 90 degrees Celsius. We're going to then dump it into some more water over here that's at a lower temperature. at 10 degrees Celsius. So same idea, when we dump this hotter water into here, remember heat transfers from hot to cold. So the hot water is going to cool down, the cold water is going to warm up. And really the heat transfer here is going from the hot water really to the cold water. So in terms of the hot water, it's exothermic, right? Negative. In terms of the cold water, it's endothermic, is positive, it's gaining all that water. So we can use sort of that relationship that Q of the, let's call it HW, hot water, minus Q of the hot water equals Q of the cold water, CW. And again, the important part when you do that relationship is having that negative in there to distribute on one side. Again, that gives you that sort of exchange of the energy. So you actually can just do, for example, minus the M of the hot water times the specific heat of the hot water times the change in temperature of the hot water. And that would equal the mass of the cold water times the specific heat of the cold water and the change in temperature of the cold water. Again, we could set them equal to each other from the idea that whatever energy that's gained by the cold water will be equal to the energy that was lost by the hot water. And again, that negative right here is what's going to help us basically kind of do that exchange of energy. So if you don't put the negative and just put them equal to each other, it's going to not work out. So you got to have that negative in there. So what we want to do is kind of put our numbers in here. So really this is our initial temperature of the hot water. That's our initial temperature, obviously, of the cold water. The mass is the 100 for everybody that's there. And even though it's hot and cold water, it's still liquid water, which means that's a specific heat capacity of liquid water is that 4.184 number that we've seen. So again, regardless of hot or cold, it's still ultimately still liquid water. So it has the same specific heat capacity. So actually putting our numbers in, we're going to get minus the mass of our hot water, our specific heat capacity. And now remember, our change in temperature is our final temperature, which is ultimately what we're looking for, minus our initial temperature of the hot water, which was 90 degrees Celsius. So again, everything here on the left-hand side all comes from the hot water part. Again, we have that negative on the outside that's going to help us with the proper signs of everything. We'll now go to the other side and do everything for our cold water, which is also 100 degrees, 100 grams. Also the same specific heat capacity. And again, final temperature, we don't know. And our initial temperature is 10. I apologize, I'm getting to the end here on my screen. So I'll go there. So that's TF minus 10 degrees Celsius at the end. So what we want to do is sort of distribute everything. So if we multiply the 100 times 4.184, we get 418.4. So essentially we have minus 418.4 times TF minus 90 degrees Celsius. And on the other side, we also get 418.4 times our final temperature minus 10 degrees Celsius. And again, I just multiplied these two guys together to get the 418. Same thing here, these two guys together to get the 418. Now we're going to distribute everybody in. So that's going to give us minus 418.4 final temperature minus our 418.4 times 90. That is now going to go from a minus, and the minus here is going to turn that into a plus. So that's important, right? So we're distributing that minus in, and that will give us 37656. Doing the same thing on the other side, we're going to distribute the 418 into each of those. Going to give us 418.4 final temperature minus 418.4 times 10. Gives us 4184, I believe. And at this point, we want to bring everybody to the correct side. So I'm going to add the minus 418 to the other side. That's going to make it a positive when it comes to the other side. And I'm going to add the 4184 to the left-hand side. So this guy is going this way. And this guy is going this way. And again, the negative becomes a positive as we go to the other side. The negative 4184 becomes a positive as we go to the other side as well. And what that ultimately gives us is gives us on the left-hand side 41840 equals on the right-hand side 836.8 final temperature. We're then going to divide the 836.8 to the other side. And what that will give us is my calculator dying. Let's try that again. Maybe it'll come back. Right here at the very end, climactic moment here. 41840 divided by 836.8 gives us a grand total of the final temperature being 50 degrees. Yeah. That is mathematically how you actually get to the 50 degrees by doing that. Any questions on that? Here I did it all together. You could have done it individually. You could have done, for example, you could have tried it. You actually couldn't in this case because you didn't have the final temperature, so you would have to kind of do it this way. Any questions on any of those steps there? Okay, so you got one more kind of similar example. So why don't you give that a go, see what you come up with. Hopefully I didn't write on that one either. There we go. All right, so how about this one? 100 grams of water at 90 degrees added to 500 grams of water at 10 degrees Celsius. And we know the answer is probably not 50. So even though they kind of give you a range here, I would like you to actually calculate the actual final temperature, what the actual final temperature will be. So take a couple of minutes, see what you come up with. Again, it's basically the same sort of approach as we've been doing these last couple of examples. on there. All right. So let's see how we're doing. So kind of the same idea here. Again, we're going to be pouring the hot guy into the cold. Again, the hot water is going to sort of lose that energy. The cold water is going to gain that energy. So again, for our hot water, going to be exothermic, and for our cold water, they're going to be endothermic. So we could again set it up equal to each other, like we kind of did in the last one. Q of the hot water, Q of the cold water, and again, we need that kind of negative in there to allow everything to sort of be correct in terms of signs. If you don't put the negative there, what you'll find usually is like the final temperatures will cancel each other out and you end up with zero, and you don't want that. So we got 100 grams for our hot water here. We got 100 grams, and we got it at it was 90 degrees, right? Yep, there, 90 degrees. And that's our initial temperature. And for our cold water, we actually have 500 grams, and that's still at 10 degrees Celsius. So we could set it up the same way. Again, minus our mass of our hot water, our specific heat of the hot water, and the change in temperature of the hot water, again with the negative sign there, going to equal the mass of the cold water, specific heat of the cold water, which is really just water, and delta T of the cold water. And in this case, if we plug it in, minus the 100 grams for our hot water, again, it really is just liquid water, so same specific heat capacity. Our change in temperature, again, final temperature, which is what we're looking at. Our looking for our initial temperature, just like the last one, going to be 90 degrees Celsius. And that's going to equal the mass of our cold water, and specific heat capacity, again, going to be the same because it really is just liquid water. And our final temperature, which is what we're looking for, minus our initial, which is 10. Any questions on sort of that setup there? Again, we're going to kind of do the same thing. So just like before, I'm going to multiply these two together, and that's going to give us that 418.4 number like we had on the last one. So again, that's going to give us minus 418.4. Our final temperature minus 90 degrees Celsius, going to equal, again, I'm going to multiply these two together, which will give us a different number. 500 times 4.184 gives us 2092, final minus 10 degrees Celsius. Again, I'm going to distribute everybody in with my negative sign here. So that's going to give me negative 418.4 final temperature, which is what I'm looking for. The minus and the plus, the minus and the negative, going to turn that into a positive, and that'll be 418.4 times 90 gives me 37656. Same thing here. I'm going to distribute this guy into both of those. So that's 2092 final temperature minus 2092 times 10, 2920 on that, 2920. Again, I'm going to bring my negative guy over here to the other side, and that's going to become positive. I'm going to bring this guy and add it really to the other side because it was negative, so it will become positive on that side when I add it. And when I do all that, I end up with 2920 plus 37656 gives me 58576 equals, again, bringing the minus 418.4 to the other side. And again, when I do that, it becomes positive. And I will end up with 2510.4 final temperature. At this point, I'm going to divide both sides by 2510.4. Again, going to cancel here, leave me with my final temperature. And it looks like perhaps if we do that, we will end up with, we'll call it 23.3 degrees Celsius, will be my final temperature. And hopefully that was one of the choices. So let's take a look back. It would be choice C here. That obviously is between 10 and 50 degrees Celsius. Question on that calculation. I'll be honest with you, I didn't really keep track of sig figs on this calculation, so we might be a little off on that. But looking at this, maybe about 2-ish sig figs probably is appropriate, I would think, like the original temperature. Any questions on sort of specific heat, also specific heat when we transfer something that's at a hotter temperature to a colder temperature? Again, the thing to keep in mind is there's that equal transfer of energy, which means if you have enough information to figure out how much energy somebody gains using that specific heat equation, that should be the exact same amount of energy that somebody lost. So that's what allows us to sort of do this sort of equal sort of exchange of energy. And as you can see here, the important thing is really those signs, because for example, in this calculation, having that extra negative allows things to be correct. And also doing this part here where we take final minus initial, also really important. Again, if you don't do it that way, what you're going to find yourself is, in most cases, you're going to be like subtracting when you should be adding, or adding when you should be subtracting, again, because your signs are off. And, that will usually send you in the wrong place. So people have a tendency sometimes just to do larger temperature minus smaller temperature. And again, you need it in certain cases for sure, final minus initial, and having that negative sign there or not there to do the sort of the math correctly. So just don't jump into large temperature minus small temperature. Otherwise, it could cause you some problems in a more complicated sort of calculation. Any questions on specific heat as I apparently heard the page there? Yeah. Okay. So obviously, we talked about specific heat capacity, and the correct units, as we saw in a couple of examples here, is obviously C is the correct unit here, joules per gram per degree Celsius. And I will say that, as I might have mentioned, I think last week as well, very common, people always want to kind of do these guys in the wrong spot. So remember that when you do Q or something like that, it has just either joules or calories, 1 unit. This is the guy here, the S, the specific heat capacity, that has, all 3 of those units. So it's very common. People will sometimes always put those guys in the wrong spot. Okay. So we're going to talk a little bit more about heat and energy here, and something that's basically what is known as enthalpy. And enthalpy is a thermochemistry type of value, and it's used in what's known as thermodynamics, which you'll talk a little bit more about delta H in 1A and then 1B as well, some of the other stuff. But the enthalpy really is sort of the it really is thought about as sort of the heat flow that occurs as a result of sort of a chemical reaction. So this oftentimes is a way that exothermic or endothermic is sort of displayed in a chemical reaction or with a chemical equation. You oftentimes are given the delta H value. And delta H is a state function. So we talked a little bit about state functions earlier. State functions, again, are things that are independent of the pathway, which means, again, ultimately, it could take one step to get to the end product. It could take multiple individual reactions to get to the end product. But, it doesn't really matter sort of how you got there. When we talk about things that are state functions, usually the only 2 things that are super important is where you started and where you ended. So kind of your final and your initial states. And that's why a lot of things that are sort of state functions, the way that you calculate it is take final minus initial. And in a reaction, products are your final and your reactants are your initial. So that's why we oftentimes will calculate the delta H in that fashion. Now, when we do things at constant pressure, which is pretty much in person, usually what you do, because you're sitting in a room that's at a constant pressure, the pressure of the room is not typically changing or anything like that. When we calculate something like Q, like we were just doing, using that equation that Q equals ms delta T, that is actually equal to the enthalpy. So the delta H value or the enthalpy value will be the same as the Q value in a constant pressure sort of condition. And usually delta H has units of kilojoules. There's actually a table, which we don't get into, I don't think, too much in here, but in the back of most chemistry books, if you look it up, you will see a table, usually delta H values. There's also delta S values, there's delta G values. These are all thermodynamic type values. And you can look a lot of these values up in tables. And in terms of the common units that are associated with delta H values, it is kilojoules. Now, when you do see a delta H value given to you in a chemical equation or reaction, and it is negative, it means the same thing as it does when we were talking about Q being negative. It means that that process is exothermic. So again, if you see a delta H that is negative, doesn't really matter the actual value of it, just the actual negative sign will indicate that that reaction is an exothermic reaction. Heat and energy is being released. And same thing, if you look at the delta H value and it's given to you and it's a positive number, that means that that process is an endothermic value. And again, the actual number or value doesn't really matter. It is actually just the sign. So again, when it is a positive value, that will tell you that heat and energy is being absorbed by the system. And you could determine exothermic or endothermic simply by looking at the delta H value, and is it positive or is it negative? So for example here, if we have this reaction, S plus O2 goes to SO2, the delta H is minus 296 kilojoules per mole of SO2 that's formed. Calculate the heat release when 2.1 grams of sulfur is burned in oxygen at constant pressure. So let's go through sort of some of this here just to kind of help you out with this calculation. And it might not make a lot of sense yet because we haven't talked about some of this stuff, but it is chapter 10, so they assume that we've talked about some of this stuff. So what we can basically know is that for every 1 mole of SO2 that's formed, there's minus 296 kilojoules of energy released. So you could really use this as a conversion factor. You could say that the delta H, for example, every minus 296 kilojoules and per mole. Mole is a unit that's common in chemistry. We'll talk about how you get there in just a second, apparently, since we're looking at this. Or you can really flip it around and use it like a mole is minus 296 kilojoules. So you can kind of use that value in a calculation like this as sort of a conversion factor. The problem is we have this guy in grams. So grams and moles, they don't cancel. So they do have to be converted into the same unit. And to do that, we would convert our grams to moles. So you may be asking, where do we convert our grams to moles? We take the 2.1 grams of sulfur, this 3206 or 7, depending on your periodic table, comes from the periodic table. So if you look on the periodic table and you look underneath sulfur, you probably see it say 3207 to be honest with you, but we'll go with 3206 since it's on the paper. This number on the bottom is what is known as the molar mass. And the molar mass has units of grams per mole. So when we take that number off the periodic table, the 3206 or 07, depending on your periodic table, that means that there are 3206, we'll just use that number that's here, 3206 grams of sulfur and 1 mole of sulfur. So we could use that as a conversion factor to get rid of the grams, although they do have it backwards here. So this looks very backwards in terms of what they're doing here. So I guess that's bad why we don't use the textbook things, I suppose. So this is not going to cancel out in terms of units, right? So we actually need to divide by that. So what we would want to do is take 2.10 grams of sulfur. We're going to divide by the molar mass. So we're going to put the grams on the bottom, which is 3206 grams per mole of sulfur. The grams will cancel each other out. And what we will end up with if we do that is 2.10 divided by 32.06 That will give us 0.0655 moles of sulfur. So what we just did here is a very common conversion. We'll talk about it in a chapter coming up of converting grams to moles. And again, this number comes from the periodic table. It is the number that is underneath the symbol. And when you see that number, when you look at that number on the periodic table, that is how many grams there are per mole. So it's always 1 mole, and the number is always the grams part of it. So again, just like we did there. So for example, if you looked at hydrogen, it says 1.008. That means there's 1.008 grams per mole. For hydrogen would be the molar mass of hydrogen. And again, you could flip it around if you needed to. Now we're going to use our relationship that we had for our delta H, that for every mole, there was minus 296 kilojoules that was given off, and that is our delta H value. So our delta H value and the moles here are going to cancel each other out, and we will end up with, let's see if at least their number was right. So at least their number was right, that's good. So 19.4 kilojoules. And the number would be negative, right, because of the negative that's here. So it would be minus 19.4 kilojoules. This is not set up right. This should be reversed like what we have here. Question on that calculation there. So you can use the delta H, and in this particular case, as you can see, a mole of sulfur, which is 32 grams, would give you 296 joules of energy released. Here, we're not using 32 grams of it. We're only using about 2 grams of it, which is way less than a mole. And that's why the value of energy that's going to come off is a lot less. It's about 19 kilojoules versus the 296 that we would expect if we threw in there 32 grams of it. Any question on that calculation? So why don't we try this one here? Consider the combustion of propane. Assume that all of the heat comes from the combustion of propane. Calculate the delta H when 5 grams of propane is burned in excess oxygen at constant pressure. I'll spit that out. I can get in it there. So I'm going to help you through this one because, again, we really haven't talked about grams of moles, so I want to show you how to kind of do it. So what we can actually get when we look at this equation, and something else that we'll talk about in a later chapter, and again, they sort of assume you already hit those chapters because we skipped to chapter 10. When you look at the coefficients in the equation, so for example, this is 1, this is 5, this is 3, and this is 4. One way that you could look at those coefficients in the balance equation is you could say that's how many moles there are of each of those things. So in this equation, we could say there's 1 mole of the propane, which is the C3H8. It reacts with 5 moles of O2. It produces 3 moles of CO2 and produces 4 moles of H2O. So that's one way we could kind of describe what's going on in this chemical reaction. So what this says is, based on propane here, we get out basically minus 2,221 kilojoules of energy for every 1 mole of propane. And again, the 1 mole comes from here, the coefficient. And since it is 1 mole, we don't have to actually put the 1, but you can if you want. But for 1 mole of the propane. If we were doing this for oxygen, what we would say is, if we were doing this about oxygen, we would say that we get minus 2,221 kilojoules of energy for every 5 moles of oxygen, which is where the coefficient comes from. Okay. But in this case, we are looking at propane, so we're not looking at that. But just to show you that you want to incorporate that coefficient into this sort of value here. Now, because this is moles, we could also use it the opposite way. We could also say that in a mole of propane, we get out minus 2,221 kilojoules. So we could really use it kind of like a conversion factor. And we do have 5 grams of propane. So again, we're going to need to convert grams to moles. And again, to do that, we have to use the molar mass. And that comes from the periodic table. And this is a little bit different than the one we just did because there's a couple of things there. If we look at the formula as C3H8, which means that when we go to the periodic table, we want to look at carbon. And if you go to carbon and you look underneath carbon, it will say 12.01. And if you look at hydrogen, like I wrote on the other page, it will say 1.008. And again, that is the number underneath the symbol. And that's the molar mass. And what that means is when we do carbon here, there are 3 of them. So 3 times 3 times the carbon, which is 1201. Do it again. 12.01 grams per mole. We're multiplying it by 3 because there's not just one carbon in this formula, there's actually 3 of them. So we need to add up the mass of all 3 of those carbons. We're then going to add it to the mass of all 8 of the hydrogens from the periodic table, 1.008 grams per mole. And if we add all that together, that will give us what is referred to as the molar mass. And this is 3 times 12.01 plus 8 times 1.008. That gives us a molar mass for propane of 44.09 grams per mole. And typically when you calculate something like molar mass, you usually go to 4 significant figures is typically what you do. And really we're going to use molar mass as a conversion factor. So just like we did in the previous one, we're going to start with the 5 grams of propane. We're going to get rid of the grams. So grams are on the bottom. So we want to put the grams part of this number on the bottom, which would be 4409 grams per mole of propane. The grams will cancel out. And if we divide 5 divided by 4409, that tells us that we have 0.1134 moles of the propane. So this calculation is really just to get it in the right units so that we can now use our energy conversion factor. And in this case, we want to multiply it by that conversion factor we really got from the equation, that there are minus 2,221 kilojoules per mole of propane. And that's going to allow the moles of propane to cancel each other out. And if we multiply that by 2221, gives us something like minus 251. We'll call it 252 maybe. 252 kilojoules of energy should be released in this case when we do 5 grams of propane. And again, you can see 5 grams of propane is less than 44 grams, which is a mole, and 1 mole of it, which would be 44 grams, gives us 2,000 kilojoules of energy. Only 5 grams of it, if we put it in there, will give us, you know, a fraction of that energy, which is 252 kilojoules. Question on that calculation, again, may not be 100% some of it because we haven't got to some of this stuff. So
yeah, I've got a question.
Yeah.
So how do we know to put the moles propane over the kilogram, the whatever it is? Like at the top, the negative 2,221?
Yeah. So really, the real way of sort of expressing the delta value is this guy right here on the right, which is the minus 2,221 kilojoules per mole. But that's something you could kind of use like a conversion factor, which is why I said you could, if you needed to, flip it the other way around. So for example, in this question, we're kind of given the moles, which is why we use the one on the right. But you could have another question that said, you know, how many grams of propane would give you like 500 joules of energy or kilojoules of energy. And in that case, you would need to kind of use that value like this with it flipped the other way. So it's just sort of the true sort of expression of the delta H would be the minus 2,221 kilojoules per mole, but it's a value that you could kind of use like a conversion factor, and it really is sort of dependent on the question that's being asked. So in this question, we really, although they gave it to us in grams, we were starting with moles. So just in a sort of dimensional analysis way, we need the moles in the opposite location so that they cancel. And opposite of that is, like I said, if you were given a question where you said how many joules you started with or kilojoules you started with, and you wanted to find how many grams, you would need to kind of use that as a conversion factor, kind of flip the other way. So a lot of things that are values, you could kind of think of it like conversion factors, and you can kind of flip it one way or the other, depending on the calculation that you need to do. Other questions?
Yeah, thank you.
You're welcome. Okay, so for us, I think at this point, you know, if I were to give you a problem like this, I would probably give it to you in moles to begin with, because we really haven't talked about grams and moles sort of conversions at this point officially. So if you are given something in moles, like I said, you could kind of think of the delta H value like this as sort of like a conversion factor, and you just want to think about it in a dimensional analysis way as to, you know, getting those proper units to cancel each other out. Any questions on that there? All right. So one common way that we could sort of calculate the heat in a chemical reaction is through what is sometimes referred to as calorimetry. And you could use a very fancy equipment to do calorimetry, but you could also use a very simple equipment, which is 2 coffee cups. So in the lab, and we'll see it, I think, next week or the following week, something like that, when we see that experiment. A very simple way to make a calorimeter is to put 2 kind of styrofoam coffee cups together, and it's pretty well insulated in that case, a lid, very much like the picture that you see here. And a lot of times what we do is we do the reaction in the coffee cups, and we follow the change in temperature of water. And we follow the change in temperature of water because we know the specific heat capacity of water, which is 4.184 joules per gram per degree Celsius, and that's liquid water. And most reactions that we do, if you ever seen equations, and we'll talk about it, you'll see things that say aqueous next to it. And what aqueous implies is that it's a water environment. So we oftentimes could just follow the change in temperature of water, or even a reaction that's happening, and we could use the specific heat of water and really calculate the energy that's happening, again, using Q is equal to our MS delta T. And because this is usually done, as we talked about, sort of at constant pressure, when we calculate Q, as is said in that other sort of slide there, that is really going to allow you to calculate the delta H. So very simply, with a couple of styrofoam coffee cups, you could do a pretty good reaction and experiment and figure out, you know, the delta H that's happening for a reaction by really just kind of throwing everybody together in a couple of coffee cups together, follow the change in temperature that's happening. Now, another sort of thing that involves delta H, and again, we're just going to go into this a little bit, and when you go to take 1A, you'll see a lot more of this, but this is the idea of what's known as Hess's law. So Hess's law is basically the idea that delta H and energy is sort of a state function, which, as we've been talking about, doesn't matter if, you know, it takes sort of 1 step to get to the end, 2 steps, 3 steps, 4 steps. The important part is really where you start and where you finish. And what that means is a lot of times when we think about reactions, we sometimes think about reactions as it must happen in, you know, just a straight old 1-step process. We're going from reactants, which is on the left-hand side, to our products, which is on the right-hand side. And it just obviously just goes straight across right there. And a lot of reactions really don't happen that way. A lot of reactions happen in a lot of individual sort of steps along the way. So for example, if we had A plus B goes to C plus D, and then C plus D goes to E plus F. Now let's just say that the delta H for our top guy here had a value, and the delta H for our bottom guy also had a value. So I'll just write it over here. So let's say the delta H for this guy was 20 kilojoules, and the delta H for the top guy was 30 kilojoules. If we add these reactions together anything that's on opposite sides of the arrow that are the same can either completely cancel out or reduce down. So we have C on the left and C on the right, so they will cancel out. D on the left, D on the right, they will cancel out. And then everything that is on the left-hand side of the arrow and everything that's on the right-hand side of the arrow will stay on those sides. And if we add this together, we get A plus B goes to E plus F. So although this reaction up on top may appear it just happens in a one-step process, here we can see that it actually happens in multiple steps. Now, when I want to figure out the delta H for this guy, I can simply add up both of these guys together. So top guy was 30, bottom one was 20. So the delta H for our overall reaction would be 30 plus 20 are 50 kilojoules, would be the overall energy that's required in this reaction. And sort of the idea behind Hess's law is that you take a bunch of individual reactions and you pretty much try to build a reaction that you're looking for. And when you build a reaction that you're looking for, you pretty much add up all the delta H's for all the individual reactions, and that will give you the delta H for the reaction that you're looking for. Now, there's a couple of things when we do this that's important with delta H's, and I'll just do it here. If you have a reaction such as A plus B goes to C plus D, and the delta H value is 10 kilojoules. Sometimes you may not need one of everybody, but maybe you need two of everybody. So if I went across and multiplied everybody by 2, what that happens with the delta H value is we would also multiply it by 2. So the delta H value, when I multiply that equation all up by 2, the new delta H value for this guy would be 20 kilojoules. And so sometimes you need to multiply an equation by a common number. And if you do, you should multiply the delta H value by that number. And the opposite is true. Let's say I started with the 2A, 2B, 2C, 2D equation, but I only really needed one of everybody. I would need to divide everybody here by 2. And if I do, I get back to the top guy. And that means that I would divide my delta H by 2 and go from 20 back to 10. The other common thing is sometimes maybe you need C and D on the other side and A and B on the other side. So sometimes you have to reverse an equation. So if you take C plus D goes to A plus B, what that does is to the delta H value, you change the sign. So it goes from positive 10 to minus 10 in this case. So those are the three sort of common things that you sometimes will have to do the equations. If you need to reverse it, you change the sign of the delta H. If you need to multiply by a common number, you multiply the delta H by the common number. And if you need to divide by a common number, you divide the delta H by a common number. So these are some things that you have to kind of keep track of what you're doing. So here, the reaction also can be carried out again in 2 processes here. And again, if we sort of add these guys together, the 2 NO2s will cancel. And this will give us our overall reaction that we're looking at, which is what this guy is. And when we add this together, the 180 plus the minus 112, we get an overall delta H for that reaction of 68 kilojoules. So really Hess's law is sort of like a puzzle. You kind of got to sometimes flip a reaction, multiply by a number, divide by a number. And the ultimate goal is to take all those individual reactions, add them together to get an overall reaction that you're looking for. And once you've done that, what you want to do is pretty much just add up all the delta H values there. And as you can see here, although this reaction, when you look at the overall reaction in the box, appears that it just does it in a one-step type process, you can see here that it actually occurs in multiple steps to get there. And that's a very common process that occurs. Like I said, most reactions don't necessarily go just in a one-step fashion to products. Could be several different ways that reactants get to the products. All right. So as I mentioned before, if you reverse a reaction, you need to change the sign of the delta H. If you multiply by a common number, you need to multiply the delta H value for that guy. Or if you divide by a common number, you need to divide the delta H value. All right, so why don't you take a try here, take a go at it. The goal is we're using these two equations and these two delta H values. You want to build this equation in the box, and you basically want to figure out what the delta H value of that equation is. So why don't you give it a try, see what you go with. I will try as well. I'll get there hopefully in the same spot. And again, it may require you to reverse a reaction, which means you need to change the delta H value sign. It may require you to multiply by a common number, which you then need to multiply the delta H value. It may require you to divide by a common number, which then you need to divide the delta H value by that. Okay, so since we're getting to the end here, let's take a look at it. We'll just kind of show you really sort of I think probably the easiest way to approach these things is not to make it overcomplicated. So really in the end, what your goal is to get everybody on the correct side, right? So what I mean by that is, for example, if I were to do this problem, which I will do right now, if I were to do this, the first thing I would look at is the first equation that's given to me, and I see NH3. And the first thing that I see about NH3 in my overall equation is it's on the right-hand side, and right now it's on the left-hand side, which ultimately means I need to reverse this reaction. So the first thing I would do is just take the top reaction, and what you want to do is reverse it. So we're going to go with 1/2 N2. And reversing just means the guys on the right go to the left, and the guys on the left go to the right. 3/2 H2 gives me NH3. Now, when I reverse that reaction, what that means is my delta H value goes from positive 46 to negative 46 kilojoules. In addition, not only did I need to get the NH3 to the right-hand side, I only have one NH3 there, and I have 4 in the final guy. So to fix that, I need to also take this guy and multiply it by 4 to give me the right amount of NH3s that I need. When I do that, I'm going to multiply 4 to everybody. So 4 divided by 2 is 2N2. 4 times 3 is 12. Divided by 2 is 6H2. And 4NH3. What that does in my delta H now is I already made it negative because I reversed it. I then need to times it by 4 as well. And that will give me a delta H value for that kind of fixed reaction of 4 times minus 46 gives me minus 184 on that kilojoules. Any questions on that so far? So again, I'm just fixing this first equation so that I get everybody sort of on the right side. Now, when I come to the second equation, when I look at H2, I don't see it in the overall reaction. I look at O2, I do, and O2 is not on the left-hand side, it is on the right-hand side. So for the second equation, I also need to reverse it. So when I take that second equation, I'm going to reverse it, which means the 2H2O will go to the left, the 2H2 will go to the right, and the O2 will go to the right. What happens with my delta H now is it goes from negative 484 to positive 484, again, because I reversed it. I will also see that I now have the O2 on the correct side, but again, I need 3 of them, not 1 of them, which means I then need to take this equation and multiply it by 3. When I multiply it by 3, that will give me 6H2O goes to 3 times 2, which would be 6H2. And finally, 3 times O2 would give me 3O2. My delta H in this case has now become positive 484, and I multiplied by 3. So I need to multiply that by 3 as well. And that will give me 484 times 3. Gives me 1452 as a winner there. And what will usually happen if you do something like I just did there, you will get everybody else to fall into place. So now if I add these 2 reactions together, so this is the guy, I'll just put a box around it here. These are the 2 that I fixed. I'm going to cancel out anything that's on opposite sides of the arrow that shouldn't be there. They're the same. So 6H2 on the right, 6H2 on the left, so they cancel. And I think that is it. That's going to give me an overall reaction of 2N2 plus 6H2O. That's everything on the left-hand side of the arrow. Right-hand side of the arrow, 4NH3 and 3O2. So that's all good, right? We have exactly the equation that we're looking for. We have 4 NH3s on the right, 3 O2s on the left, on the right as well, 6 H2Os on the left, and 2 N2s on the left as well. Now, in terms of the delta H for this guy, we're going to basically take our 2 values and we're going to add it together. So what we had for our first equation was the delta H was minus 184 when we did all of our adjustments. We're then going to add it to our second equation when we did all of our adjustments, which was 1452. And if we do all that, that gets us 1268 kilojoules as the overall delta H for that reaction, which is right here. That value is a positive number, which will tell us that this reaction is endothermic because it is positive. Energy is being absorbed in this reaction. So sometimes people get really kind of lost when they're doing these type of things. You do want to sort of just keep it simple, and the easiest way to do that is like, I need this guy on the right-hand side or this one on the left-hand side. And as you could kind of see what I just did there, we kind of fix one thing and you kind of put them together, pretty much everybody else will sort of come into place the way they should and fall into place in terms of their numbers. Any questions on sort of Hess's law there? Okay, let us stop there. We went a little bit long, so We will start lab about 12:05. Give everybody a little extra time to kind of stand and stretch. And we were doing the second part of physical chemical changes, I think, today. So I think that's experiment 6. We'll do another example as well next time. And make sure you put here, and we will see everybody in about 10-15 minutes.